Hey, John here. Let's take a look at modules today, their ports, the parameters, the local params, just to make sure everyone's in sync when we start creating these things. Today I'm going to talk about their ports, the fact that they're input, output only, and in-out. We've seen some of these before if you watch my channel. I haven't used these yet. The parameterizing of modules very, very useful because you don't want to create a counter that can count to 100 and then have to create a whole nother module to create counters that count to some other values. Because my point is there's usually an adder in such a module, and the number of bits that you need in that adder, the counter, will depend on how high the value is that it needs to count to. So you can create modules that have parameters to let it know how big of a number you want to use, and it can reconfigure itself, and that's the key here, based on these parameters. So that's what we're going to look at today. As always, a big thanks to all my subscribers and thumbs uppers and Patreons, especially the VIPs shown here. Let's go to mod 0 and see what we got going on in here. Okay, we got a test bench file that we're going to use to go over these details. Some of this we've already seen, so this should hopefully fill in some gaps that could be fodder for misunderstanding, right? So here are the rules. A module definition cannot nest, and by that it means between module here and end module down here, we cannot define, you won't see another module being defined inside here. You can, in a single file, as you see here, have another module down here. These are not nesting. This is simply two modules, one after another, in one single file. That is legal, okay? So that's what they mean when they say module definitions cannot nest. The definitions cannot. However, the instantiations of such things can. By that I mean this. Here's how you instantiate a module. Let me give you a quick rundown of this earlier on. This is a test bench module, even as I've named it in a way that suggests that, right? We're all familiar with these things, right? And inside here, we create an instance of the module you just saw down here. Mod 0 is the name of that module type down there. And we create one like this, and we'll get into the details in a minute, this whole point of this video. And that's what I mean by an instantiation. And by nesting, okay, instantiations, what I mean is inside the test bench, the top level module of this test bench, I'm instantiating a module. Inside here, I don't, but I can, if I want to, instantiate one or more other modules inside here. And in that way, I mean, just like calling a subroutine, in some ways, right? In a regular old program, you define a bunch of functions. In this case, they're modules. These are circuits, really, right? And these can encapsulate other circuits, just like a subroutine can call another subroutine. So that's what they talk about when we say an instantiation can nest, but module definitions cannot. Therefore, what do we got? All modules have names that are in the global scope. So a side note, let's talk about scope a little bit today. Where is the module name TB valid to be used? The answer is anywhere, because all modules have names that are in the global scope. Global be anywhere in your program. Anybody, anywhere can instantiate an instance of the TB module, if you want to. So what's the point of pointing this out? Well, don't name them like an idiot, okay? Think about the life expectancy of your project. If you're professional, it will be 100 times longer than you expect. And if you expect it to be in several years, it'll be 100 times less than you expect. It always seems to be the case, right? What is my point? Well, my point is don't name it something terrible. When I name a test bench like this, I'm expecting it to be the only one in the universe when I run. a simulation to test usually to test another instantiation of some module that I want to put under this test case here. Okay, so I pretty much always name those things TB. Otherwise, this is a really crappy name for a module. And mod 0 is probably not a good one either, but for sake of discussion and education, it's a perfectly reasonable name. What I'm getting at is you should pick names that will, at least be expected to live throughout the life period of your project. All right, as you add more stuff, you don't want to end up with all these colliding names. An instantiation of a module will be given a name that is what we call in a local scope. So what happens is this mod 0 is instantiated, and we'll talk about all the noise in here later on, but here's the name of the instance. Mod 0 is I create 1, and I'm going to call it AAA. And you could say, if you've ever taken a college entrance exam, that mod 0 here is to AAA here as reg is to clock 1 up here. So clock 1 is an instance of a reg data type. That's how we do this. And down here, the AAA is an instance of a mod 0 module. So this is the instance, this is the type, and the instance name is where we're getting at with this. The AAA is valid only within the context within which it is defined, which is this module here, which is the TB module. It is local, we say. The scope of that is local to the TB module. Okay, so that's what this line here means. I'll observe that the top level module is instantiated, because how does this ever come into being, right? Who creates that, right? Who's the prime? What's the prime mover? It's instantiated during synthesis. When you give the compiler, there's a command line option. If you look closely at the make files that I create, when we're using Yosis, and if you're using, the Xilinx ISE or Vivado, there's usually, you specify this is the top module, okay? And you'll see that in your build environment. During simulation, I'm using Icarus. Verilog is Icarus, okay? It's the name of the simulator. The way it works in there is that, and I cut and pasted this right out of the doc for Icarus. Icarus Verilog will, by default, choose all modules that are not instantiated anywhere else, in your design, and use those as the top level. All right, so it just infers it. It figures it out. Not always the best idea, but, and if you don't like it, you just read the manual for Icarus, and you can see in there, there's I think it's -S or something. You can specify the name of the top level module that Icarus will instantiate, and therefore, in doing so, it'll walk down here and say, oh, in order to create a TB, I have to create a mod 0 called AAA, and then it'll go down here and see if it needs to make more, blah, 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 and build this giant hierarchical tree out of all the instantiations before it starts running the simulation, okay? So that's where these come from, how they get created, and the definition and how the word scope is used in, casual conversation when you're out for a beer after work or something. All right, so we've seen test benches before. We know that regs and wires have different meaning. A wire is of type net. If you read the Verilog specifications, and reg is merely a type of variable. It's different than a net. And I want to punch this again right now, because we're going to see this in a few minutes when it comes to instantiating our modules. There's some rules about how the ports work, is my point. All right? If I haven't done this before, note that when you create a reg, you can assign it an initial value right then and there. So as I say over here, by the way, this is the same thing as if in some initial block somewhere, because you can be more than one in here, right? It is the same as at time 0, simply saying clock 1 equals 0 in an initial block. So you can put all that together and get noise out of your initial down here if you want to. And this is useful for FPGAs if you're studying Verilog for other types of designs that don't have static memory that is loaded when the chip starts, like an ASIC or something like that. Then you cannot do this. I mean, some of the rules, the limitations of Verilog change depending on the type of technology that you're using it to target. All right. So anyway, if I haven't mentioned that before, that's what that means. Obviously, you cannot assign a default value to a wire because you can only assign a wire one and only one value, one and only one time. Somehow, somewhere, like an continuous assignment statement, or we'll see in a minute, this particular one is assigned a value by this module down here. All right, so let's see what we're doing here. What's going on? We've got 2 clock signals and a wire, a net called the value. We fire up our app. We save our simulation variables. We wait 100 clock ticks and shut her down, okay? We have to shut it down, otherwise it'll run forever. I think I talked about that once before, because these things will never stop running. You have to kill this somehow, and that's why this is here, okay? In case you forgot, or you're joining this series already in progress. So what do we got here? We got 1 clock that runs on every tick, and another clock that runs once every 3 ticks of the system timer. Okay, that's fine and dandy. And what do we got here? So here's us instantiating a module. I've shown you these before where I simply say, here's my module type, and then I give it a name, and then we connect up the ports. No problem. Notice what I'm doing here. There's this pound sign followed by some crud in parentheses. It looks like I'm doing the same thing twice. And the grammar in here matches the grammar down here. These are when we assign the ports, okay? This is what we do when we're assigning values to parameters, overridable parameters, I could say, all right? Let's go down and look at the module and then come back up here and look at this because it'll make more sense in the context of what we're actually creating by all this stuff, okay? What do we got down here? A little notes to myself. It's okay to define more than one. I already talked about that. Aha! This module is defined using the ANSI style grammar and syntax, okay? I use this, and I think everybody that's modern uses this. But I'm going to show you another way of doing this in the next example. And I want to hit this point and make sure we've seen it and talk a little bit about it because the other method is messy and confusing. And if you're looking around the internet, you will see older code using the older style. And if you don't know how to read it, you'll be in trouble. Okay, and maybe we'll talk a little bit about it and you'll be convinced you don't want to use it either. I mean, the language was out there more than a decade before they allowed this style of using it. And while this isn't great, it's certainly better, way better, in my opinion, than the other style. So we'll come back to that in a few minutes. Alrighty, so what do we got here? Parameters. It's all about these things, these parameters. Again, you see this pound, open paren, this hash, if you want to call it that. Parens, and then you see the parens we're already familiar with, these down here, which represent the ports for this module. These are the parameters for the module with the pound in front of it, and the ports don't have a pound, and they're just parentheses that sit here like this. Okay, and white space is generally ignored in this language. So, in theory, this whole thing could be one big long line, minus these comments, of course. If you wanted to, all right? I tend to write my code like this so I can comment each thing. In this example, the comments are about the grammar and style that I chose to give you examples, so I remember to mention them. Normally, you'd say what the heck a P1 is, and please document your code. It's constantly finding code with no doc whatsoever, as if everyone on Earth knows exactly what your intentions were when you wrote it. Seriously, you look at your own code more than a year from now and you have no idea how the heck the thing worked. If you're a genius and you do, then I salute you. I will buy you a beer. Next time our paths cross, ask me for that beer. No one does this. Everyone's code reeks when they don't document it. Just doc your freaking code, all right? So, what is the doc in here for? Okay. Parameters must have values that are compile time constants. By that I mean you either assign it a literal, or you can assign it using some sort of an expression that the compiler itself can resolve before it compiles or while it's compiling your program. If I say P4 equals P1 plus 4, the compiler can figure that out because it knows the value of P1. It's right there. All right? These are compiled time. They have to be resolved to values before the compiler can compile your code. And then once they are set, the value is known, it must remain constant forever after that. There is no way during runtime to change the value of a parameter. Period. Okay? That's what we mean by this. It has to be knowable when the thing compiles it, and it must never change afterwards. All ports, I think I mentioned this before, must be input, output, or in-out. I should probably put the formal name in here instead of abbreviating it like that. I'll push this out before I release the video so you get the right doc. Only output, right? Put ports may be of type reg. Okay? Now this is a something that is open to some debate of preference. Okay? Whether or not an output should be allowed to be a reg is a personal preference of a lot of people. We'll talk about the pros and cons of deciding whether or not an output should be a wire or a reg as we get into more complicated designs. Input and in-out ports must be of net type, okay? When we're doing FPGA designs, a net type means it has to be a wire, okay? And if you think about it for a little while, it sort of makes sense. The input to a module is a wire. It's a connection, okay? A reg is something that can be assigned a value from an always block, right? Well, anybody that creates an instance of this module may not be writing to an input port of this module, right? It's a sync from the perspective of the guy that instantiates the mod 0. He wants to take a signal and stick it in here. If this thing is allowed to use a reg on an input, then, theoretically, whoever creates it would have to write into it using an always block, which is just annoying. So these all have to be wires. Therefore, anyone that instantiates this can connect anything up to it, either a wire or a reg, within its own context and the scope of the instantiator. They can connect any variable or net, wire up to the input ports as needed, okay? Now, what do we got? Bunch of parameters. Generally, you see this sort of thing. Something equals constant, something equals constant. And then these are used later on in the code for whatever is, relevant to this type of module. And when you create them, you can parameterize then the function of this mod 0. You can make them, give it a range. If you want, this can be an 8-bit value. Otherwise, these are some sort of an integer value. I don't know. It probably depends on the simulator or the synthesis tool, what the default bit width of that thing is. It could scale it automatically based on this value here. It might just use 102 in decimal as the value, and then the context within which you use the P2 would define how many bits it has, and so on, right? If it matters, Give it a range like so, okay? So that's the pound sign, open paren, use a parameter like this. Then you close it, you open up another set of parens, and you got your inputs and your outputs, right? Here's an example of an output wire and an output reg, and when you're done with all that, there's a semicolon. So this whole thing is, as I said before, one single statement. And we can talk about in-outs more later on when we actually need them in a design that we're actually going to create. They can be touchy, and where Yosis is concerned, you have to do it in a certain way. Otherwise, you might end up with a problem, okay? So it really depends on the synthesis tools when it comes to interpreting the code. Okay, so we have a module. It's got 4 parameters. It's got 4 ports. Now let's go back up and see how it's instantiated. We have 3 and 3. What does that mean? I got 3 here, and I got an empty one. What the heck does that mean, right? Let's see if I can get all this on the screen at once. Of course not, because that would be useful. All right, so we got P1, P2, and P3 in here. What does that really mean? This means that P1 is to be overridden and put the value 11 into P1, rather than whatever the default is, okay? So we're overriding the default of P1. We're going to override whatever the default value is of P2. And in here, you can put P3 in there with nothing in it. And that means explicitly, I know there's a P3, and I don't want to override the default. Use the default for P3. Explicitly. Implicitly, I don't even mention P4. And that means it's going to use the default for P4. So I got 11, 22, default, and default for the P3 and P4. That's what it means. So I got 11 instead of this, 22 instead of that. P3 is going to be hex C0, which is a 192 in decimal, right? And P4 will be, what did I say, 11 plus 4. So it should be a 15 for P4 because it's P1 plus 4. All those are compile time constants, right? So what do we got here? Expression is okay because it can be evaluated at compile time because P1 is on. Note that this example may be poor practice, and by that I mean when we get into realistic things, you probably don't want to create a parameter that's dependent on another parameter unless you really want to let the person instantiating this to override P4. In other words, if P4 really does need to be dependent on P1, and the relationship really is it should be for more than P1, don't put it here because some dingus may assign P4 a completely bogus value, and maybe your module will no longer work. That's when you use a local param down here, if you want. If you don't want to let somebody override a parameter, like maybe inside my module, I have to know that P1 plus P2 is some value that I use down here, and I want to give it a name. Do it with a local param because local params must be compile time constants as well as regular parameters, but these cannot be overridden when the module is instantiated. The instantiator is free to replace these values at will with whatever they want. But when we're done, this will always equal, LP1 will always equal P1, P2 plus P2 because no one's allowed to override the definition of LP1. It can change the value, obviously. In this case, it won't be 203 because I got a 1, 1, and a 2, 2 in here, which means it'll be 33, okay, when this thing runs. That's what this means up here. And of course, you put commas between each of these things, right? Now, we've seen these before, but explicitly, think in terms of the source and the sink. Those are the words that they use in the Verilog specification. So I almost always forget and put this darn name up here next to the module name before the hash, and then I get an error, and then I go, oh yeah, I got to put it over here. Every time I do this. I mean, I don't do it every single day. This is not my bread and butter kind of language, but when I do it, I tend to need to remind myself, oh, it goes over here. Okay? All right, so what do we got here? I'm connecting clock 1 and clock 2. We saw those earlier. These are both regs up here. to A and B, the ports called A and B of my mod 0 module. Q1 is being connected to the value. Now over here, as we scroll back down, you'll be reminded of the fact that A and B are both input ports, and they can be driven, like I said earlier, it can be driven anywhere from either a wire or a reg in the context of the instantiator, which is the module within which we have this instantiation, okay? Now, Q1 is an output from the module mod 0. We'll remind that in a minute. And that thing is, regardless of the type, this thing here looks like a source in the context of the top level module here, okay? So Q1, because it's a source, this thing has to act like a continuous assignment in the context of the instantiator. So you can only drive a net, which is, a wire. Okay? And if we want to, we don't even need to use all the ports. Now, depending on what they're for, it may not make any sense to do that. But if there's an output or even an input that you don't need in your design, you can just leave it out of the instantiation. And what happens when you do that, in synthesis, in this particular case, I left an output unconnected. I don't care about the Q2 output. Okay? What happens is the synthesis understands that this is going nowhere. And when it synthesizes all this stuff here, it will automatically delete all this code. It's creating a Q2 that has no beneficial result. Therefore, it doesn't need to calculate its value. Therefore, it doesn't need to read these inputs. Therefore, this whole always block can go away. Now, it turns out in simulation, we don't have that luxury because down here it does get used because we print it out in this display down here. Okay? But if you really think about it, what does it mean to have a component on the end of in a schematic? We got some wire going on over here. You got a gate, an OR gate in this case, and the output is not connected, right? I mean, duh. You don't need the OR gate. You don't need these inputs. And if A is actually created somehow in some other circuit, but otherwise is not used, in this case it is, but if it was otherwise not used, then it wouldn't need A either, and all this optimization will start deleting things, which is actually kind of an interesting thought in itself. Sometimes when I just want to compile some code to make sure it compiles, it actually makes me laugh a lot because I might create a top level module like this. For synthesis, I create a top level module, but it has no ports. And what happens is, because a real honest to God top level module, if it has no output ports, it doesn't accomplish anything. So all of the outputs are removed and it cascades through the entire design and it's optimized away. And then the results come back and says you've used 0 LUTs and 0 nets. It always makes me laugh. The whole thing optimized my entire program away. So just be aware of that. It is smart enough to do that sort of thing. Okay. So that's what happens if you don't specify an output. You can not specify an input, and there's some rules. I generally don't not specify my inputs, but if you don't specify it, you'll have to be aware of what that means and what impact that would have to your module that you're creating or designing or using or whatever. Generally speaking, you want to specify values for the inputs, and if you want, you can ignore some of the outputs, is my point. Okay? So that's your parameters. There's your ports. Well, sometimes you can have an output that's a reg. Other times you can make them in a wire. That's all legal and fine and dandy. Whether you use a wire here or a reg will depend upon whether you want to just do a continuous assignment to a wire, which is the case for Q1, or maybe I want to assign Q2 something more nasty and complicated from an always block. Well, then it would have to be a reg. Okay, and as I said before, there's some debate as to whether or not you should ever put a reg as an output in here. We'll talk about the pros and cons of that some other time. The bottom line is, if you need to assign it a value from an always block, make it a reg. If you want to assign it a value from an assign, make it a wire. Nothing wrong with that. Everything else is style and, you know, conventions of your office and your coding team and that sort of thing. Whatever rules you wish to convey upon yourselves, okay? Now, down here I got an always block with a star in here. And I find this very interesting. I just threw it in for fun, and then I started looking more closely at it and kind of had a couple of aha moments here. It never ceases to amaze me what happens during simulation when it comes to triggering things that need to run and don't run and playing around with display versus strobe. Now, this doesn't have anything to do with the modules and the parameters and stuff, but I just wanted to throw this in. And as a side note, we'll take a quick look at what happens when we look at this using display versus strobe and what kind of confusion that can cause. If you haven't fully thought out what you will see when we play around with it in a minute. All right, so back to the beginning here. What do we got? We got a clock that's going fast, another clock that's going slow. We instantiate a module that has various parameters that are actually not used for anything other than the fact that show you how they are set. And it has 2 input bits and an output bit down here. And the Q1 and the Q2 are set. Q1 is an AND function. Q2 is an OR function. And we throw away Q2, so what we really have is an AND gate with some clocks to generate some patterns so that we can see the AND gate working, and a bunch of parameters we never use. But we can understand now how to set their values, and we will see that they are set when this display call gets done over the course of time. We print out the time, we print out the A, B, C, or A, B, Q1, Q2, all the parameters, and the local parameter values in here every time this runs, okay? So let's go ahead and fire it up. What do we got going on here? A lot of spew. Maybe I shouldn't have run it so long. Well, you can change it to 10 and get less output if you would like. However, let's have a look-see here. What do we got? Time 0, we got A0, B0, A0, B1, we got A0, B0, A1, B1, A1, B1, and so on. Look closely at this part of these lines, okay? Well, let's start with the parameters, I guess, before we get too cute with the display idiosyncrasies on the left. What I'm doing is printing out all the parameters over here, which by definition are constant during at the end of the compilation period and can never, ever change. Every P1, this column will be 11 forever, because that's what I set it to. P2 will always be 22, because and P3 is always a C0 in hex, which is 192 in decimal. P4 is a calculation, as you recall, of P1 plus P2. No, it isn't. It's P1 plus 4. This one over here is P1 plus P2, right? So you can clearly see that we were, in fact, specifying overriding the defaults values of these various parameters. P3 was not overridden. That's the default, right? And we explicitly did not override it. And P4 we did not override either, and it is set to P1 plus 4, as we can see over here, okay? Right there. And again, LP1 is calculated by adding P1 and P2. So this is how you use your parameters, how you specify them, and how you can calculate values using them. Now, while we're in the neighborhood, let's watch this thing run for a little while. We start out with 0 and 0 because I initialize clock 1 and clock 2 both to be 0, and then I connect them to the A and B ports of my instantiated mod 0, within which this is being printed. So I said these are known as A and B inside that instantiated module. We calculate Q1 and Q2. This is the AND function, as you may recall, and Q2 was the OR. So now we got a 0 and a 1, and that means this will be 0, and the OR will be a 1. We know that. Now we got A0 and B0 again, and we got no AND is 0, OR is 0. That's fine because the clocks are going up and down. Now we got A is 1, B is 1. It's interesting that Q1 is 0, because that's supposed to be the AND function, right? Q2 is a 1. The OR is correct. This is weirdo. Look at the time. Time 3. This down here is also time 3. And now we got A1, A1, and now this is right. So we have an extra shot in the always block that prints out the display function. Why do you suppose that is? It depends on your simulator. It's the way it is because these are not non-blocking assignments is why. These are combinational circuits. And a continuous assignment is very much the same kind of a thing as an always block. An always at star with these two variables that is making an assignment, a blocking assignment to the output. Except for since this is a wire, I can't put it in there literally. But it's a separate and autonomous thing that runs when the inputs change. What it means is that the AND function performed by this assign was done after the OR function code was executed in the always block down here. Right? So what happened was the OR function was calculated and assigned a value into Q2. When Q2 was assigned a value, it said, who cares about this? And he finds out this guy does because it's used down here. Q2 is hiding in this asterisk. So it says, I better run this thing. Goes on the list of things to do. Comes back and says, what else do I need to do? Well, apparently it runs this at that time. And when it's done with that, it asks, what else do I need to do? It finally gets around to running this assignment here and says, A was changed or B or whatever, and I need to recalculate Q1. And it does the AND, it calculates the value for Q1. It says, I now change Q1. Does anyone care? Yeah, the guy down here cares because he's used down here. Better schedule this thing to run. And then that second time it runs, all in the same time quanta. All right? That's why you see it literally running twice. It's an artifact of how the simulator runs. In theory, the simulator could, if it was smart enough, it could optimize out this second call if it wanted to. It doesn't have to call it twice just because two values happen to change. That's not a rule. What is a rule, it must execute at least once after a value changes. Okay? So be careful of this. It can be very confusing. Look at how often it happens. This one here did it again. It changed B from a 1 to a 0. It left A alone. And in doing so, we see the AND function will have to change. And it does. And when that happens, it schedules it to run again, even though the OR didn't change. If you look closely enough, who knows? Maybe you'll actually see 3 in a row. In theory, it could happen. Okay? So this can get very confusing if you use the display incorrectly. Now, I would not say that I'm doing it incorrectly. I put it in there on purpose to show you it changing. I mean, that's why it invoked, it processed that last always block down here. This ran twice because Q1 changed and Q2 changed, or B did, or whatever. These 4 variables change asynchronously, is what happens. So it can run more than once. So you can actually watch it evolve over the course of time. You can actually see it if there's non-blocking and blocking, and depending on the complexity of your circuit, this may never print the right value, if you think about it. If you do this, it will eventually run, remember the stratified queue, it'll run after everything settles down in the current time tick, including after all of the non-blocking assignments have completed, if there are any. In this case, there aren't. I mean, there are because the clock, is that true? No, there's no non-blocking in this entire application. This is all simple combinational type stuff. Anyway, when they're all settled down, this will then run. And that'll be confusing in another way, right? Because it'll still get double triggered. See, look at that. It's still getting double triggered. But when it is double triggered, at least it's not wrong, because it schedules both of those invocations after all of the input A and B and Q1 and Q2 values are done changing. So you can see it sneak in here and throw out a few extra prints. These two lines are exactly identical. All right, in fact, if we run it, when I pipe it through unique, it'll remove the duplicate lines. And the only ones you'll see 1, 2, 3, 4, 5, just like so. This actually might be what you would expect, is my point. But in reality, due to the simulator, the way it schedules what's going on, by detecting, oh, something changed, I better remember to invoke that always block. It queues it possibly more than once, okay? Or it'll queue it and execute it before it's done executing all the other always blocks in the same time, of the same simulated time, and then end up finding out it needs to do it again. Okay, so be careful when you interpret what you're getting that comes out of your display and your strobe calls. Right? Well, let me put this back so that I don't commit the changes I'm making with the wrong value in there. Right? Let's make sure it still compiles. Yay! All right. Any questions? No? All right. Well, moving on here. Comments below. I'm more than happy to open up dialogues and questions, or float over to the Discord. See the link in the video below, under the video on YouTube for a link to the Discord, where there's a lot of people over there that definitely know this stuff. There's some good discussion going on there. Or, Google around. Other universities have notes. I found this actually while I'm off on a tangent, because you know me, I never do that. Here's a set of slides I found where, as it says really tiny here, Verilog, Primer 1, whatever. This might be from, and this is like some random university, and I thought they had their name in here. Come on, universities, put your name on your documents. I did not write this, I stole it. And I was flipping through some of these to try and give you links and examples, but the problem is, we have, this one doesn't look too bad. Some of these use very old style grammar, which we're about to see in a minute, and it really is difficult to follow them sometimes. This one doesn't look half bad. I think this is, let me look up where it came from, since I got it in front of you right now. I'm not. I may have closed my browser window, and the answer is I don't know where that one came from. But I happen to know that University of Washington is one of the places that has some notes that I've found. Just Google around. Just type in Verilog Primer or Introduction to Verilog, University Course Notes. There's tons of these out there. You can spend an enormous amount of time reading university notes on Verilog to your heart's content, if that's what you want to do. My point in showing that is that if I give you a crummy example or I misspeak or something, it's really difficult to edit a video after you post it on YouTube. In fact, it's like impossible. I think I can remove stuff, but I can't add it. I can't, dub in some audio. And I'm not going to redo the whole thing, repost it, delete the old one along with all the comments and views. I'm sorry when that happens. And so I'm sure as everyone else with the YouTube video online that needs an edit. So if there are errors, I usually put them in the description, put some notes in the description below the video on YouTube to say, by the way, I misspoke here and there, and these are the truth, and so on. If you think I'm wrong, run off and Google around and see if you can find some other notes and specifications. And if it turns out I am, please post notes. I read them and I summarize, and I usually accumulate them in the description. Notes below the videos where you should be reading. If not mine, other people's videos do the same thing. Always look in there when it's a tutorial of any kind in case there is something that's caught and advertised as a oopsie. So you don't learn something wrong is my point, okay? So here's another test bench, and this exists for no other reason than to talk a little bit more about the style, these oldie-timey style here. Look at what I say. Here's one using the old style, annoying and error-prone. I had a lot of other four-letter words I wanted to put in here. Don't do this, okay? I think this is rancid. It's terrible. It's error-prone. If you're managing a project over the course of time, this can create problems. Subtle things can cause trouble. Now, when you're really good, you can keep your eye and be careful about it. But no. You need to see it because you need to know when you see it on the internet. If you want to use a code example that uses this style, because this was the way it was for like 15 years in the early days of Verilog. And before it was changed to the style that pretty much I think everybody uses, if not should use, today. Okay, so there's that, and I want to show you a trick that I like to use with some of the parameters and what it means to parameterize a module if it's not really clear. Okay, tried to make this as simple as possible, but it gets easier, especially when you don't use the old style grammar. Okay. All right, so this is mixing two examples into one program. Welcome to what you should not do on YouTube 101. Bear with me, I don't think this one's too bad. And then we'll move back to ANSI style and put all this behind us. Okay, so what do we got here? We got a red clock, we got a wire called reset. Usual thing here with a free running clock for my test bench. And what are we doing here? I'm creating a POR. It's going to be using a power on reset type of a module down here. Okay, so it's going to employ a couple of techniques that might be useful if you want to design them into a project. Okay. Oh, what do we got here? We got a POR module instance called R1, another one called R2. This is all about the style that I use to specify the values of these arguments. These are overrides to parameters, and these are how we connect the ports. In this case, I'm using what we call keyword assignments. I want to set the delay parameter to 3. If I don't put a keyword in there and I just put a number like this, that means I want to set the first of however many there might be parameter to 8. And if there's more, there'll be comma, blah, 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 blah. In fact, if there's, say, 3, in this case there's only 1 anyway, but let's say there's multiple, I can do this. All right, you can actually leave a hole in there. This is explicitly skipping the second one. So if I have delay and X and Y as my parameters, I would have the delay set to 8, the X would be whatever the default is in this scenario, and the Y would be set to 6 if they were defined in that order. Okay? Yeah. I love those missing ones, the blanks, not used to seeing that kind of thing. It just sets out as weird as me. And that whole thing also applies to the ports. If there's 2 or more ports, in the first 2 I want to connect to my local variables, in my local scope called reset and clock, these guys up here, I can put reset and clock in there. Whatever the first one is, I want to connect it to reset. Whatever the second one is, I'm going to connect it to clock. And order obviously matters. So down here, they're called reset and clock as well. They just happen to have the same names. This could just as easily be called X and Y down here. Like so, but of course now I got to rewrite the code below to match that name of this of the port there. So I'm going to leave well enough alone. I apologize, I should have used different names to drive home the fact that I'm not doing this, right? The clock in my local scope is being used to connect to the port called clock in the scope down here in the module POR, my instance of R2, okay? I just use the same names. I actually think there's even a notation that I never use. Feel free to look it up, throw it in the notes below. I'll stick it in the description as needed if somebody finds it. I think my point is there's a way that says just connect all the same named local scope variables to the same named ports as a shortcut. I think that is a feature in Verilog, by the way, and you might see that. So somebody, if you know what it is, let me know. And I'll throw it in the description below the video on YouTube. So, where the ports are concerned, you can use ordered list to connect them, or you can use the name of the ports in the instantiated module, as well as your locally scoped variables that you want to connect them to. And you don't need to put them in any particular order. You'll notice that these are in the opposite order of these. I did that on purpose because, obviously, if you're going to say, I want to connect the clock to this, it doesn't matter which port it is, or which order, where it is in the list of all the ports, right? It does matter over here if you're going to use the ordered parameter style specifying. And I mixed them like this in kitty corner checkerboard style because I wanted to make sure that you understand that you don't need to use the same thing consistently across all the ports and all of the parameters when you do this. But you do need to be consistent within, one set of parens. Okay, order will matter if you start using positional arguments. I almost use the word parameter, but these are ports, right? These are arguments in grammatically speaking to this operation in this expression, right? If you have two arguments and you're going to use positional specification, then order matters. If you're going to name them, order doesn't matter. If you want to name them for your parameters and use positional for your ports, that's fine. You want to use positional for your parameters and keywords for your ports, that's fine too. Okay, but you got to be consistent. All your parameters need to be the same, whatever style you're using, and all your ports need to be the same for whatever style you're using for your ports. Okay, but these style here and this style here don't have to match each other. Okay, that's what I'm trying to say there. Okay, moving on. Let's take a look at this oldie-timey style. If you've ever written ancient K&R style C code, this will look more familiar to you. Here we name all of the ports. We don't say whether they're inputs or outputs or regs or wires or anything. You just name them all. This establishes an ordered specification of the ports. Then down inside the module, you say, oh, by the way, the reset is an output, and I'm going to use a reg. Thank you very much. And if it is a reg, I can assign it a default value right inside my port list. You can also do this if you use the ANSI style, where you put the, you don't use this. You just say open paren and you put all the ports right in there, close paren. My point is, if it's a reg, you can assign it a default value right inside your port list if you want, if you're targeting an FPGA, right? And then down here, I can say, clock is an input. And I didn't bother to tell you what kind, because the default is a wire. So if you see somebody saying input clock, it will be a wire, because the only thing that's allowed to be a reg is the output. And I can leave reg off of here if I wanted to, but if I did that, reset would then be of type wire, because wire is the default. Okay, is that, I hope, perfectly clear? So in the old style, what you did is you named them all and you gave it the order in which they appear, if they're going to use ordered assignments, which I think is all they ever used to have in the old days. And then you have to later on inside the module somewhere tell it whether it's an input or an output, which means you get to rename name them all twice, which is a lot of typing and a waste of time. Lovely, right? So that's the oldie-timey style, and that's what that means. Now, how do parameters work if you don't put the # parenthesis thing up in here? And there's the beauty of it. Anything that declares itself to be a parameter anywhere in your entire module, this could be all the way down here, okay? That is a parameter, period. They don't all have to be up here. They can be strewn all over the place. And here's the great, even better, the order in which these parameters appear in throughout this entire module. If there's 5 of them, and one's here, and one's down here, and you might have some more down here, that specifies the order of the specification of them if you use the ordered list style instantiation of them up here. Isn't that cool? All right. So, in other words, if you're like editing code and you decide to remove a parameter or move it up here, you could then change the order and that all these happening up there. That's horrible. Okay. If you put them all up here at the beginning of your function, my point is, you're less likely to accidentally reorder them or add one or delete one and change the relative position of them amongst each other and so on. Just don't do that. You want to put them all up here so that if somebody wants to use it, it's all staring them in the face. They don't have to read your entire undocumented, more often than not, code to try and find them all in here. You actually have to open up an editor and say, search for parameter, please. Because, some people are just slobs. And look, there's one hiding here and there and so on. To search, do a text search in here to find them all. Just no. So that's why I don't use this. Don't use it. Don't give me any code that looks like this. Please don't. If I'm way out of line here, let me know, because I think this is terrible. All right, so now we get to the stuff that's not as terrible, and this is why you need to have a way to parameterize a module, even if you use oldie-timey style. And mind you, this is a relatively small module, so even if you used oldie-timey style in here, it's not that bad because you can actually find it. But as they get bigger, it can be problematic. Now, let's say this is okay. So the point of this is a power on reset module. And a power on reset module is a module that will assert the reset output signal for the period of time given by delay number of clock rising edges. So as designed with these default settings, this thing, when the FPGA boots up, will assert reset for 10 clock periods. Then it will take reset to 0 and then stop doing anything. So this is just going to generate for some period of some number of clock ticks long period of time. It'll assert reset and then it'll deassert it. Okay, so this is a power on reset generator type of thing. That's what I had in mind here. Okay, so how do you figure out how many bits you need in your counter? I was talking about this earlier. Well, that's the ceiling of the log base 2 of the number that you're using for your counter. In other words, in order to count to 10 in binary, I need to have CLOG2 number of bits in my counter. Actually, plus 1. If I want to get to the number 10 from 0. All right, I'll leave it as a test to the viewer to try and figure out the off by 1 problem in here. In fact, I test it. Okay, notice that 3 is 1 less than a power of 2, and 8 is a power of 2. If you don't do this right, you may not be able to count up all the way to 8, because you need 4 bits to count to 8, not 3. Okay? My point is, you need to make sure you have enough bits in your counter to be able to count up as high as you need to go. And getting the bits right, if you don't know how to use this, requires a test bench. Okay? We'll break it and we'll show you what happens if it doesn't work right, just for fun. Okay? Because, this video isn't already gone into overtime. Okay, so what do I got? Now, I'm foreshadowing another subject called finite state machines. This is the style I use, which I adopted from Pong Shu, which is, there's some links in one of my websites about, things you can read, some documentation resources as I look around my desktop while vamping, as it were, looking for these notes here. I'll put a link to all this in the description below. on YouTube, my Verilog notes. This is like a reading list kind of a thing. Links to various documentation, the standards. I think I've shown this before in this playlist that will include this video, this guy here, Pong Shu, and this guy, Clifford Cummings. When we get rolling and we get some real code going, these guys' notes, his Cliff Notes series, these are really good advice, okay? This guy seems to know what he's talking about. We'll look at some of his papers a little bit later once we get to writing some, real code, and we need some higher level advice. These guys here are, you could do worse, okay? Anyway, my point is I'm using a style that this guy proposes. It's not necessarily the same style that other people use. I've seen floating around on YouTube and other example codes. Everybody's got their own style. I'll leave it at that. We can talk about them to some degree. Join us on the Discord. And honestly, I'd love to hear your opinions. I'm more than happy to change my style if somebody has a better one. This one works for me. And by that, I mean this. We have a sequential circuit up here. What we're describing here are some flip-flops. Okay, the pause edge of clock, I want to set the counter to whatever the next value is supposed to be in that counter. And it may make sense. I got a power on reset and I got a counter. It's going to count. So I calculate the next value for the counter using a combinational circuit down here. We'll look at it in a second. And then I assign that value when the clock ticks to the counter flip-flop. I do the same thing for the reset signal. I'm generating the reset signal. I'm going to, it's going to start out as a 1, as you can see right here. By default, when the FPGA boots up, it's going to be asserted. That's what that initial value is going to do in there. And while this thing runs, every time there's a positive edge on clock, the new value, the next value, after the rising edge of the clock, will be calculated by this logic down here, the combinational circuit down there, and be made ready so that it can be assigned to the reset output signal. Okay? And that's what you're seeing in here. I got a counter, which is the current value of the counter, and then I have a counter next. I got a reset and a reset next. The reset's up here, remember? Reset is a reg, reset next is a reg, counter is a reg, counter next is a reg. And that's because all these are assigned values in these two always blocks. Okay? Now this is a 2 always block style finite state machine design. This one doesn't even have a reset. It's the thing that generates a reset. But I don't want to get philosophical about it. Okay? The simple fact of the matter is, when this module is instantiated and it fires up, right, when the system starts running, whether it's in simulation or synthesized code running in an FPGA, it starts out with reset next equal to 1, and it starts out with reset equal to 1 because it needs to be asserted, because that's what power on reset does. Maybe I should have called it the initialization time resetter. That would be more accurate for an FPGA, right? In any event, I digress. So let's look and see what's going on here. The end result is that in this style, and we'll get much more into the details of this, and even Cliff's notes over there has some opinions on it in different styles, okay? As does Pong Shu. So this is a 2 always block, finite state machine. The one up here does nothing else other than use non-blocking assignments to say, update the flip-flops with the values that are needed to be put in there on the positive going edges of the clock that runs the finite state machine. The combinational circuit down here exists for the sole purpose of asking, what is the current state of the system? And given that current state, as well as any inputs, but this doesn't have any inputs. I mean, you could say it has a clock input right here, right? But that clock input serves not this combinational circuit down here. It serves the purpose of synchronizing the output, right? And the counting operation, okay? But the input to the combinational circuit down here is nothing other than the counter itself, okay? And we ask, is the counter equal to the delay value? In other words, has it counted enough to get to the point where we no longer want to reset anymore? Counter starts at 0. Does it equal delay, right? By default, it's 10, right? And I think we create one that's got an 8 or something in it. Has it gone up as far as it needs to go? If so, turn off the reset signal. We're done resetting. Then we ask ourselves, what should the next value of the counter be when that happens? Well, the answer is it should not change value anymore because we don't want this to ever not be reset anymore. Okay? So the counter has to stop. If it keeps going, the reset might go back on again when the counter wraps around back down to 0 and so on, right? Okay, so this thing says go until counter equals delay. At that time, turn off the reset and stop counting. It will cease and lock up in this state, as it were, okay? If that's not the case, we know we must be counting, and therefore the reset should still be on, and the next value of the counter should be whatever the current value is plus 1. So the whole point of this is to say, I need to know what should go out of this circuit down here on the counter and reset signals the next time there's a positive edge on the clock. When the clock ticks, positive edge, counter next will have been calculated down here. It'll either not change or it will, but it'll be in counter next. It'll be in the counter next variable, and it'll get copied over to the output of a latch and say that's the new counter value. Same thing with reset. It'll either be changed to a 1 or it'll be set to 0. And that will also be assigned to the output of this module down here. Okay? So this is a relatively simple state machine, by the way. They can get very ugly, very complicated, a lot of opinions. More than happy to read about yours, the comments below. This is about as easy as I could make one for this stage in a discussion in the amount of time I gave myself to put this together, which is about 20 minutes. Okay, so what do we got here? I got 2 of these. One of them has a delay of 3, one of them has a delay of 8. So I'm instantiating 2 of these reset modules. If we run this, we look at the plots, we should see one that waits 3 ticks and then goes off, another one that goes 8 ticks and then goes off. Okay? And the clock, of course, is going 1010101 every time the simulated time advances 1 nanosecond. All right? So there's no display, there's no real output to be printed, but we can plot it. And now we can look and see what we see if we have a system with multiple modules. So the TB is your top level module, and it instantiated 2 POR modules. One's called R1, and the one's called R2. And if you look at R1, it says here's the stuff in R1. It has a, what is that, 2 to 0. That's a 3-bit counter and a 3-bit counter next. If we go to R2, notice these values change. This is a 4-bit counter and a 4-bit counter next. That's because the parameterization of our POR circuit, that module, had different delay values. And it self-configured the counter with that C-log2. Let's see, go back here. This C-log2 in here, in this local parameter, to figure out how many bits it needs in order to count up to whatever the delay value is that you use when you instantiated it. This is the whole point of this. Let's not get too caught up in the finite state machine and all the other stuff. That's why we do this. If I put 1,000 in here, it would need 10 bits. Just for fun, let's do that. Okay? So we open up the plotter. We should see what's going on here. We should see 10 bits in the P2, and it's 0 through 10, which is 11. Well, there's a sophomoric mistake right there. Who saw that coming? All right, this is classic. How many bits do you really need? All right. When they go down to 0, this should be -1, okay? Now, here's the problem. Okay, if I want to wait 8 ticks if I start from 0, I need to count up to 8 minus 1, right? Because the 0th count is part of my delay. So as designed, this currently will wait delay number of clock cycles plus 1. And in all reality, if it does need to wait delay plus 1, it might need num bits down to 0. But if we want it to delay the correct amount, we want this to be minus 1. Okay, I screwed this up. And this down in here needs to say if counter equals delay minus 1. This is a very classic problem. I'll leave it as a task to the viewer just to work this through and convince yourself that I'm right at this point and I was wrong before. And I'm not going to re-record this video because of two things. Number one, everybody makes mistakes. And number two, this is a very easy one to make when you're not thinking and you're yakking on YouTube, making sure that all these still work. What was the one we did for counter number 1? Go back around, edit the thing. It's supposed to count up to 3, which is, yeah, that's a 2-bit number. 3 is a 1-1 in binary. So it does make sense that this is counting to 2. Okay, so if we count, oopsie, I added this to the screen. I guess if you double click on here, it adds it to the screen. You can do it like this if you want. And the delay, the reset timer should go, once it gets to the value that we're talking about, it should go off. And it does. Do I have the clock in here? No, dingus. So what do I got in here? This one counts 1 cycle, 2 cycles. The third cycle, well, it sort of ends here because the clock starts low. If it started high, this would be part of the first cycle. So it could be off by half a cycle. Or it could be long by half a cycle, okay? So, again, this is all part of how you want to design the initialization sequence and all this fun stuff. But this does count up to 3 and then stops, right? You can actually see the counter 0, 1, and 2, and then when it would otherwise go to 3, it deasserts the reset on this edge, okay? Whoops. It doesn't matter if you want to wait longer or count longer, but you might need more bits. That's all that matters, right? So this one now is going to count up to like 1,000 and then clear itself way over here. And it's in hex. Oops, come on. 1,000 is just shy of 400 in hex. But if you don't know what it is in hex, you can go over here, right-click on data format and go decimal, please. And you can see it goes from 0 to 999, which is exactly 1,000, right? And on the next leading edge after it's 999, the reset signal deasserts. You can also see it deasserting over here in the reset next. Because remember that bottom always block is calculating what is supposed to happen on the next rising edge right there based on the current value of the counter. By the way, if you have a hard time seeing stuff in here, what do? You say data format, blah, 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 highlight, alias. No. You go over here and you say view, show wave highlight. See, this whole horizontal bar now lights up. So if you got a lot of stuff on your screen and you want to look far over to the right and you want to talk about this on YouTube, you can do that. Okay? Just another couple of tricks about this particular viewer. Anyway, and there's other viewers as well. People are talking about viewers that can automatically decode I2C and all kinds of fun stuff. So learn how to use those tools is my point there. Okay, so anyway, 0 to 999 is in fact 1,000 total. And when it gets to 999, the bottom always block is starting to analyze and decide what the next value is supposed to be because it's down here at that time. Actually, no, it's right here because when counter equals 999, this is true. And it says the next reset signal should be to turn it off, and the next counter value should be not to change anymore. And if we look closely, this line down here is my counter next. And let's put them both to decimal because that can be very confusing. All right, you can see that the next value is based on the current value by adding 1 to it, right? So the current value here is 998 plus 1 is 999. That's what it should be stored in the flip-flap. That's what you see getting copied up there. When the current value is 999, is my point, this guy over here becomes true. And it says that the next reset signal from here on in, it should go to 0. And the next counter should no longer change anymore, right? That's what we were talking about. And you can see down here, 999 never changes again. And the reset signal says the next tick should go low. And on the next tick, it does go low. So if we, I suppose if you really want to test this, if I really want to embarrass myself and risk screwing this up, we should run the simulation a whole lot longer than that. Let's run it 5,000 to make sure that there's nothing weird down here where it stops running and then it starts going back and resetting itself. You know how that sort of thing happens, right? Open this up. Now we have a much longer run time, and it better not sneak back on again. And it does not. You can see the power on reset is high, then it goes low, and it stays low. Okay, so here's us debugging a design that I managed to screw up. I'll commit the correct files because, you know, they should be right. Typical off by 1 kind of a problem, all right? And you actually see this a lot. I can't believe I left num bits in there rather than doing num bits minus 1. That was kind of foolish because I do this all the time. Normally it's I use these for like how many address bits do I need for a memory that has this many bytes in it and things like that. Or in this case, like counters and stuff like that. In my defense, I redesigned this program. I used to have the counter count up to delay all the way up to delay, so it had 1 extra count in it, and I was using the counter as part of the state machine, and that got ugly, and then I added the reset, whatever. Anyway, moving on. This is what happens when you evolve your code, right? If I'm wrong, by the way, and I have extra bits in here, and I'm right down here and do this right, that 1 extra bit is what I was talking about earlier. The synthesis code will figure out that it never changes, number 1. And you never use it, number 2, and it will optimize it away. It probably will optimize it away. Sometime down the road, we'll play around with this stuff and watch the output of the synthesis. I don't have a make that will actually synthesize this, so we do it now. If we had another hour. My point is we can look and see how many LUTs it uses and that sort of thing. So this is correct as it sits right now. And one last check on the way out the door. Let's look at the first one because we look at the second one. Let's look at this guy here and make sure he doesn't sneak back on again either, right? Because that would be embarrassing, right? So you can click this to say put it all on the screen at once, please. Wow. Okay, so what are we doing here? We can go to the beginning, thank you. He goes high and then he goes low right there, and it's so far over to the left you can't even see it in the bigger picture here. So yeah, it does work after the 3 or 4 ticks or whatever it is. 3 clock cycles, and goes off and stays off. So that's not a screw up. And by the way, if you want both of these to go at once, you can do that. You can just simply add them both, right? And get them all on here. You can just keep adding and adding and adding. You can go up in the test bench, and over here you can add its clock, which we already see in here, and this reset itself, which is weird, actually. What the heck? This is totally insane. It's unknown here, and then it's low there. This is wild. I made another mistake in here. And I am not going to start over again. This video is long enough as it is. What the heck did I do? I assigned reset to both of them. Wow, I got 2 outputs driving the same wire. The reason this is not a compiler error, which you think it should be, is because Verilog, remember, can be used for things other than FPGAs. And this actually is a good point, although I did not want to bring it up right now. In other systems, what happens is Verilog will implement like a wired AND gate or a wired OR gate. Or you can actually say that the output from this module has a stronger drive capacity than the one up here, and that therefore the output from this one can overdrive and become stronger than the one up here, and therefore become dominant. So this is this is really bad. So the simulator may have done something weird. It does show that it was an unknown state because it was red in the waveform analysis. That's just weirdo. What I should have done is this. I'm a dingus. My fault. I'll commit this as well. This might make more sense. This is a rough day. Bad weekend. It's been raining. You'd think I'd have plenty of time for this, but no. I had to go out and shovel sawdust out of the lawn before the grass died because I had some tree trimming done, you know, the usual stuff. Now, we have two resets. You can see them both. There's one of them going low, and the other one is the short one on the far left. This is a little embarrassing. How many mistakes can you make in one YouTube video? I'm sure I've done worse. Yeah, by now I've got 300 or 400 videos, for crying out loud. Find the mistakes in John's videos. On that note, I think I will bid you adieu. The short of it is, we've got the parameters, local parameters, and ports, and the inputs and the outputs, and the knowledge that they have to be compiled, time, constants, and things like that for the parameters. That's been covered. Now, can I design a power on reset module that works on the first try in 20 minutes while getting ready to record a video? Apparently the answer is no. But I can work my way through it, and that's why we do these test benches. This is a great example, by the way, of how to evolve a correct solution by using test benches and understanding the waveforms and what it means to have, drive conflicts and all that. Wow! I should have done this later in the series, but jeez. These are realistic things that happen, especially while you're learning and you make mistakes like that, whatever. So, yeah, sure, that's my story and I'm sticking to it. I meant to show you what happens when things screw up. Why not? Because you're going to probably have mistakes you need to debug on your own, and you need to recognize what they look like. Thanks for watching. I'll see you next time, maybe with a better set of examples. My finite state machines are next. Google around a little bit. That reminds me, if you make it this far, if you go to look at the playlist for this video series on YouTube, I can even find it myself in less than an hour and a half of looking. If I go to my studio, this is like, hey, I got a YouTube channel, and I can click on stuff and see comments and posts. Here's the playlist where I put all this stuff. I think I hit this thing, and then I hit, where are the videos in this list? Here they are. I added, or I'm going to add, see these down here? More and melee state machines. You want, an asynchronous counters. These two videos are from some lectures, some university lectures that I gave some years ago from another playlist is my point. These things you want to brush up on if you're not already up on how finite state machines work. And there's a link in here that goes to my faculty page over here, which is this thing here. And here, there's the syllabus and all this other fun stuff. Last time I taught it was in fall of 2022. And all these links down here. Here we go. This is what if you need more background and binary and floating point, bitwise, and all the combinational, sequential. I don't teach FPGAs in this course, but this is about just simple Boolean logic and what does it mean for a computer to actually do stuff using finite state machines and counters and stuff like that. So this is what these links in the playlist go to, this section right here, and where I talk about how counters work, and you just saw one that I didn't do right in Verilog, sorry about that, and how finite state machines work. There's some handouts. I even designed this lecture on purpose to use the same exact example of someone else's video that they had posted years earlier on YouTube. And the reason I did that is because if you don't understand my description in this video up here, you can watch the exact same example being described by somebody else. And if I really stink at it, you can just abort my YouTube channel and go watch someone else's. But, you know, sometimes, my point is sometimes two explanations, different explanations of different vantage perspectives on the same subject can be much more useful, especially if you're missing something subtle that may not get conveyed by either me or the other person giving this lecture down here, okay? So what also happens is I've got some handouts. We'll be looking at these diagrams in the next video when we walk through and implement them using Verilog. So anyway, the point is, if you go to the playlist, you can see, how do we get back to the playlist here? Where are the videos? Here we go. And you see these synchronous and asynchronous counters and the melee and more style finite state machines. You want to know the difference here. It's a big deal, and it will impact how you want to design your code in Verilog, okay? So in this video, there is, here you go. This is the link, the direct link into my site that goes to the handout right here. Is my point. Whoa, it's bigger than the screen that I used for recording. And it give these little diagrams in here, and this is going to be important when you design your state machines in Verilog. In newsflash, you basically can't do too much useful stuff with an FPGA if you don't have a state machine. When you think about it, combinational circuits, you got your inputs, you got your outputs, you know, an address decoder or something like that, fine. But you want to count, you want to talk to an SPI device or an I2C, or do anything interesting over the course of time, you're going to need a finite state machine. And this is what it's all about, okay? And there's two different styles, and you need to decide which kind you want to use, given the kind of problem you're trying to solve. So you may want to, if you don't already have a really good understanding of finite state machines, have a look-see at this, you know, maybe watch the other lectures up here, or this one down there, or somebody else has it. So, at this point, I'm babbling on, and I can see the sun came back out, so I can get back into yard work. I'll talk to you later. See you next time. Thanks for watching.